Hello friends, welcome to my first lecture on solution of Lagrange equation. We know that an ordinary differential equation has solutions which involve a few arbitrary constants. If you take another ordinary differential equation, then its solution involves, general solution involves n arbitrary constants. Now in the case of a partial differential equation, we have solutions which involve arbitrary functions, and so by particularizing the arbitrary function, any number of arbitrary constants can be inserted, and therefore we can say that a partial differential equation is richer in solutions than an ordinary differential equation. Now let us define what do we mean by a complete integral. We know that when you eliminate two arbitrary constants, we obtain a partial differential of first order, differential equation of first order when there are two independent variables. In my last lecture we have seen that when we eliminate the two arbitrary constants, we obtain a partial differential equation of first order in case of two independent variables. So a relation between the variables which satisfies the partial differential equation and contains as many arbitrary constants as there are independent variables is called as the complete integral of the given partial differential equation. Now a solution obtained by giving particular values to the constants occurring in the complete integral is called as a particular integral of the given partial differential equation. Now we also in the previous lecture we have also seen that when we eliminate an arbitrary function phi from the relation phi u b equal to 0, where u and b are independent functions of x, y and z, we get a partial differential equation of the first order, and therefore when a partial differential equation of the first order is given, we will have a solution phi u b equal to 0. This solution is called as the general integral of the given partial differential equation. Now we can generalize this to the case of n independent variables. When we have n independent variables, the general integral is a relation between the variables involving n minus 1 independent functions of those variables together with an arbitrary function of those n minus 1 functions. Now let us define a similar solution. The equation of the envelope of the surfaces represented by the complete integral is found. This equation of envelope is called the singular integral of the given partial differential equation. Now this singular integral differs from the particular integral in that it cannot be obtained from the complete integral by giving particular values to the constants. Let us say we have the partial differential equation fx by z pq equal to 0, which has been derived from the relation fx by z ab equal to 0, where a and b are two arbitrary constants. We know that when you eliminate the two arbitrary constants occurring in the relation fx by z ab equal to 0, what you get is a first order partial differential equation. So fx by z pq partial differential equation is derived from the relation fx by z ab equal to 0. The envelope of the surfaces represented by the equation 2 is found by eliminating a and b, the arbitrary constants a and b, between the equations fx by z ab equal to 0, delta for delta equal to 0 and delta for delta b equal to 0. Now singular integral is a relation between the variables involving no arbitrary constants. In general, singular integral, if it exists, it is distinct from a complete integral, but in the exceptional cases it occurs as a particular case of the complete integral obtained by giving special values to the arbitrary constant. This is also in the exceptional case. Now let us see how we get the singular integral from the partial differential equation directly. Suppose we have the partial differential equation of first order fx by z pq equal to 0, then the singular integral when it exists is obtained by eliminating p and q between the equation f is equal to 0, its partial derivative with respect to p and its partial derivative with respect to q equated to 0. So on eliminating p and q, we shall obtain a relation between x, y, z which will be independent of any arbitrary constants, and this relation is a singular integral provided it satisfies the given differential equation. So now let us see how we can obtain general integral from the complete integral. Let us say the complete integral of the differential equation b fx by z ab equal to 0. So here x and y are taken two independent variables and we have two arbitrary constants. So we have defined the complete integral as the solution involving as many arbitrary constants as there are independent variables. So in the relation, so here this can be called as a complete integral. So fx by z ab equal to 0, let this be the complete integral, and one of the constants, suppose a, can be written as a function of b can be written as a function of a, say b equal to phi a, then we can write the complete integral as f(x) by z a phi a equal to 0. The general integral is then obtained by eliminating the constant a between equation 2 and equation 3, which is the equation delta f over delta a equal to 0. The equations 2 and 3 represent the curve of intersection of two conjugated surfaces of the system f(x) by z a phi a equal to 0. The envelope of the family of surfaces is the locus of the intersections of conjugative surfaces and hence contains the curve. So, this curve is called as the characteristics of the envelope. Thus, the general integral may also be defined as the locus of the characteristics. Now, let us see how we find the solution of a partial differential equation. While solving a partial differential equation, we must not only find the complete integral, but should also indicate the singular and particular general integrals. The partial differential equation is not said to be completely solved if we just find the complete integral. We shall now discuss how to solve a partial differential equation of first order and first degree. So, Lagrange's method of solving a first order and first degree partial differential equation provides such an integral involving an arbitrary function, and this solution this integral which involves an arbitrary function, it provides all solutions of the partial differential equation which are not of the type known as special functions. So, this we shall see later on. This case where a solution of the partial differential equation is not actually contained in the general integral. So, this we shall see later on. It is just an exceptional case where all solutions of the partial differential equation are not obtained from the general integral. Now, hence the partial differential equations of the first order and first degree is considered as completely solved if the solution of the differential equation is obtained by the Lagrange method in the form phi u v equal to 0. Let us see the most general form of the Lagrange first order and first degree differential equation. So, Lagrange linear equation is an equation of the form p p plus q q equal to r. Let us remember that this small p represents the partial derivative of z with respect to x, and this small q represents the partial derivative of z with respect to y. So, where this p, q and r are functions of x, y, z. So, thus we have a first order and first degree differential equation, and we have seen that by eliminating the arbitrary function phi from phi u v equal to 0, we find the partial differential equation p p plus q q equal to r, where p comes out to be equal to this and q comes out to be equal to this and r comes out to be equal to this. Hence, when we have an equation given by 3, let us say when we have an equation given by 3, we have an integral given by equation 2, this integral. So, when we consider a partial differential equation of the first order and first degree, its solution will be given by phi u v equal to 0, which will be called its general integral. Thus, our problem is now reduces to finding the independent functions u and b that occur in equation 2. If we know the independent functions u and b, then we shall be able to write phi u v equal to 0, the general integral of the given partial differential equation of first order first degree. So, let us now consider the equations u equal to a and v equal to b, where a and b are arbitrary constants. So, then on differentiating, what do we get? U equal to a gives you delta u by delta x, because u is a function of x, y, z. So, delta u over delta x dx, delta u by delta y dy, delta u by delta z dz equal to 0, because a is a constant, and similarly b equal to v gives you delta b over delta x dx, delta b over delta y dy plus delta b over delta z dz equal to 0. Now, let us solve these two equations. So, solving these two equations, we get we obtain dx over uy minus uy vz minus uz by and then dy over uz vx minus ux bz. And then we have ux by minus u by vx. Okay. Now this is equal to, this is p, so we have dx over p equal to dy over q equal to dz over r. So then on solving, then on differentiating the equations u equal to a and b equal to b, we arrive at the subsidiary equations dx by p equal to dy by q equal to dz by r. The equation 4, the equations 4, these equations, there are two independent equations. So there are the equations 4 are differential equations whose solutions are u equal to a and v equal to b. Hence, to obtain a solution of the partial differential equation pp plus qq equal to r, we write down the subsidiary equations dx over p equal to dy over q equal to dz over r, and find two independent integrals of the subsidiary equations, say u equal to a, v equal to b. Then the general integral of the partial differential equation will be given by phi ub equal to 0, where phi is an arbitrary function. Now since we are only interested in an arbitrary function relating u and b, we may also write the general integral in the form u equal to psi b, where psi is an arbitrary function. Now this can be generalized to the case of n independent variables. Suppose z is a function of n independent variables x1, x2, xn, and we are given the partial differential equation p1 delta z by delta x1 plus p2 delta z by delta x2 pn z delta z by delta xn equal to r, where p1, p2, pn and r are functions of the variables x1, x2, xn and z. Then we form the subsidiary equations dx1 over p1 equal to dx2 over p2 equal to dxn over pn equal to dz by r, and obtain the n independent solutions u1 equal to a1, u2 equal to a2, u1 equal to an of these subsidiary equations. Then the general integral of the given partial differential equation is written as f u1 u2 u1 equal to 0, where f is an arbitrary function. Now we are considering a special type of Lagrange linear equation, where we shall see that some solutions are not actually obtained from the general integral. Such solutions are called as special integrals. For example, let us consider the partial differential equation p plus 2q z to the power 1 by 3 equal to 3 z to the power 2 by 3. So this is a Lagrange linear equation, where we see that capital P is equal to 1, capital Q is equal to 2 z to the power 1 by 3, and R is equal to 3 z to the power 3 by t, when we compare this equation with the Lagrange linear equation general form. So the subsidiary equations are dx over 1 equal to dy over 2z to the power 1 by 3 equal to tz over 3 z to the power 2 by 3. Now our aim is to determine two independent integrals u equal to some constant and v equal to some constant from these subsidiary equations. So let us see, this is very simple, because we can apply the method of separation of variables. So we have, let us consider the equations dx over 1 equal to dz over 3 times z to the power 2 by 3. So when we integrate this equation, we get x equal to 1 by 3 z to the power minus 2 by 3 plus 1 divided by minus 2 by 3 plus 1. So this will be plus some constant, let us say a. So this will be equal to 1 by 3 z to the power 1 by 3 divided by 1 by 3 plus a. So this can be cancelled, and we have x minus z to the power 1 by 3 equal to a. So we have got the function u x by z as x minus z to the power 1 by 3. Now similarly, let us consider dy, another equation, dy over 2z to the power 1 by 3 equal to dz upon 3 times z to the power 2 by 3. So then we shall have dy equal to 2 over 3 dz upon z to the power 1 by 3. Now again let us integrate, integrating we get y equal to 2 by 3 z to the power minus 1 by 3 plus 1 divided by minus 1 by 3 plus 1 plus some constant, let us say b. So this will give you 2 by 3 z to the power 2 by 3 divided by 2 by 3 plus b. So this will cancel and we get another integral y minus z to the power 2 by 3 equal to b. So thus we have two independent integrals u x by z equal to x minus z to the power 1 by 3 equal to a constant a, and bx by z equal to y minus z to the power 2 by 3 equal to b. Now we can see that these two functions of x y z are independent of each other. So hence the general integral is given by some arbitrary function phi u b. So that means u means x minus z to the power 1 by 3 and y minus z to the power 2 by 3 equal to 0. Now we note that, so we have got the general integral by applying the method given by Lagrange. Now let us notice that the differential equation p plus 2q z to the power 1 by 3 equal to 3 times z to the power 2 by 3. It is also satisfied when we take z equal to 0, because when you take z equal to 0, then this will give you p equal to 0, its derivative with respect to x equal to 0 and q equal to 0. So p equal to 0 and q equal to 0, when you substitute and z equal to 0, the given partial differential equation is satisfied, and the z equal to 0 cannot be obtained from this general integral. It is not an, it cannot be expressed, z equal to 0 cannot be expressed as a function of x minus z to the power 1 by 3 and y minus z to the power 2 by 3. So such a function is known as the special integral. So there are some exceptional cases where we notice that a solution of the partial differential equation is not expressible as a function of the independent integrals u and b. It cannot be obtained from the general integral. Now let us take one more case. So let us consider one more partial differential equation of this kind, p plus q times 1 plus z minus y to the power 1 by 3 raised to the power 1 by 3 equal to 1. So again we see that it is a Lagrange linear equation. So we can write the subsidiary equations. The subsidiary equations are dx by p. Now capital P here is 1, so we have dx by 1, capital Q is 1 plus z minus y to the power 1 by 3, so we get dy upon 1 plus z minus y raised to the power 1 by 3 and dz upon r is equal to 1. Now we have to find two independent integrals, u equal to constant and v equal to constant from this subsidiary equations. So let us first solve dx over 1 equal to dz over 1. So this solving this, we get x equal to z plus some constant a, or ux by z equal to x minus z equal to a. Now let us find the other solution. So we can consider dy over 1 plus z minus by raised to the power 1 by 3 equal to dz upon 1. Now this is also equal to dy minus dz divided by 1 plus z minus by raised to the power 1 by 3 minus 1. So this cancels with this. So thus we have r dz upon 1 is equal to dy minus dz over z minus by to the power 1 by 3. Now let us define z minus by equal to some variable t, then dy minus dz, or dz minus dy is equal to dt. So we shall have dy minus dz upon z minus by to the power 1 by 3 we can write as minus dt upon t to the power 1 by 3. Okay. Thus dz upon 1 is equal to minus dt over t to the power 1 by 3. Now let us integrate. So integrating we have z equal to minus t to the power minus 1 by 3 plus 1 divided by minus 1 by 3 plus 1 plus some constant b. This is equal to r z equal to minus t to the power 2 by 3 into 3 by 2 plus some constant b. So this also can be written as minus 3 by 2 z minus by to the power 2 by 3 plus b, or we get u v x by z equal to z plus 3 by 2 z minus by raised to the power 2 by 3 equal to b. Thus we have got two independent integrals, u x by z equal to x minus z equal to a, and b x by z equal to z plus 3 by 2 z minus by to power 2 by 3 equal to b, and therefore the general integral of the given partial differential equation, which we can write in short as PDE, is phi u b equal to 0, that means x minus z and z plus 3 by 2 z minus by raised to the power 2 by 3 equal to 0. Okay. Now this is the general integral which we have solved by which we have obtained by solving the subsidiary equations. Let us notice that if you take z equal to y, okay, so we note that if z is equal to y, then due to the independence of the variables x and y, when we differentiate z with respect to x we get 0, and when we differentiate z with respect to y we get 1. Okay. So if you look at the given partial differential equation, p is equal to 0, q is 1, and then z is equal to y. So we will get 0 plus 1 into 1 plus 0 equal to 1, and therefore z equal to y. So the equation is satisfied. And therefore z equal to y is also a solution of the given partial differential equation. But we observe that z equal to y cannot be expressed as a function of the functions independent integrals u and b. Okay. So, since z equal to y equal to or z equal to y cannot be expressed as a function of u equal to x minus z and b equal to z plus 3 by 2 z minus by to the power 2 by 3, it is called as a special integral. It is a special integral of so thus in some particular cases of partial differential equations we observe that there exists a solution which cannot be expressed as a function of the independent functions of x, y, z, u and b. Otherwise, in almost all cases the general solution integral which is obtained from the subsidiary equations includes all the solutions of the given partial differential equation. So, this is what we have about the about how we solve a Lagrange partial differential equation of first order and first degree. In our next lecture we shall discuss in detail this method of solving a linear partial differential equation of first order and first degree, and we shall also give the geometrical interpretation of the Lagrange first order and first degree linear differential equation, that is PP plus QQ equal to R. With that I would like to conclude my lecture. Thank you very much for your attention.